Hi everyone, in this video, Group 4, we will talk about geometric sequence, virus spreads in early pandemic stage.
A geometric sequence is a sequence of numbers where each term is found by multiplying the previous term by a constant value. This constant value is called the common ratio R. So, a geometric sequence is in the form AR squared, where A is the first term and R is the common ratio of the sequence. The common ratio can be either a positive or a negative number. Formula for n term: AN equals to ARN minus 1, where A is the first term and R is the common ratio.
In the early stage of pandemic, virus spread occurs without intervention. Each infected person infects a fixed number of people, causing rapid growth. This situation can be modeled using a geometric sequence. But how? This assumption allows us to model the spread virus mathematically. Look at the day 1, day 2, and day by day. That is how fast virus can spread to people per day. For this slide, I want you to imagine how a virus spread at the very beginning of a pandemic. We start with just one infected person at the top. That person doesn't just stay alone, they pass the virus to other 2 people. Now, here's when it becomes serious. Each of those people then infect 2 more, and this process keeps repeating. So the number of infected people goes from 1 to 2, then 4, and then 8. In mathematics, this pattern is called a geometric sequence, where the common ratio is 2. What this tells us that the growth isn't linear, it's exponential. From the table, we can see that the number of infected people doubles every day. On day 1, there is 1 infected person. On day 2, there are 2 people. On day 3, there are 4 people. And this pattern continues. Because the number is multiplied by the same value each day, this situation can be represented using a geometric sequence. The formula for a geometric sequence is AN equal to ARN minus 1. In this case, the first term is 1 and the common ratio is 2. For example, to find the number of infected people on day 5, we substitute n equal to 5 into the formula. Then calculate, got 16. This means there are 16 infected people on day 5. By using the formula, we can estimate the number of infected individuals after n days.
To build our model, we define our parameters based on the official data from March 2020. First, we set our initial term A as 50, which was the number of cases on 4 of March. The common ratio R represents our transmission rate, and AN represents the cumulative cases after n intervals. Now, let's look at the mathematical model. The spread follows a geometric sequence formula, AN equals A times R to the power of n minus 1. Here, A is our starting point. On 4 of March, we have 50 cases, so A equal to 50. By 16 of March, which is our 5th time interval, the cases increase to 553. To find our growth factor R, we substitute these values into the equation. Then we take the 4th root to find the common ratio. This gives us an R value of approximately 1.823. This means the virus was spreading at a rate of 82% per interval.
So now we can see the divergent pattern. This reflects the high transmission of the virus during the early stage, showing a clear divergent pattern in our geometric sequence. This model represents the average multiplicative growth over the selected time interval. The calculated R equals to 1.823 implies that during this early phase, the virus spread at a rate of approximately 82.3 per time step. The high ratio highlights the high infectivity of the virus when no social distancing measures like MCO were yet in place. The doubling time TD is given by TD equals to 1.23 times unit, as shown in the formula below. This indicates that during the early outbreak phase, the number of confirmed cases in Malaysia approximately doubled every 1 to 2 times intervals, consistent with rapid epidemic growth. Next will be epidemiological interpretation. The geometric growth observed corresponds to high effective reproduction number, RT, during the early pandemic stage. Factors contributing to this rapid increase include lack of population immunity, absence of vaccination, high contact rates, delayed detection of cluster. While the geometric sequence does not directly estimate R0, the growth factor R is positively correlated with transmission intensity. It is important to acknowledge the limitation of using geometric sequence. For example, real epidemiological data is noisy and not perfectly geometric. Testing capacity and reporting delays affect confirmed case counts. Growth rate change following interventions. The model is valid only over short early stage intervals. Therefore, this model is descriptive, not predictive for long-term dynamics.
You may ask why this model is only useful for early pandemic stages. Well, at the beginning, infection tends to grow by a roughly constant ratio from one period to next. This happens when the whole population is susceptible. Under this condition, cases increases proportionally over time. Factors such as lockdowns reduce the effective transmission rate. Consequently, growth is no longer constant as it might slow down. In conclusion, this study shows that a geometric sequence can model the early spread of COVID-19 in Malaysia, when cases increase at an almost constant rate due to the lack of immunity and limited interventions. The large growth factor reflects how quickly the virus spread in this initial phase. However, because the model assumes a constant growth rate, it becomes inaccurate once control measures are introduced. Therefore, geometric sequences are only suitable for short-term, early-stage analysis, highlighting the importance of early interventions in controlling outbreaks. Thank you.